So, would you mind if we resume a little bit earlier? Yeah? So, in terms of planning, I'm going to skip the hands-on sessions that we would have, and I will move all of them to the end, so that if you are too tired from probing stuff, we can stop. But on the other hand, if you want, we can spend the end of the afternoon doing the exercises, right? So we can. So very quickly, there are many ways to prove. Well, there might be more than one way to prove the exercises. The first one, what I did was I performed universal instantiation of X, the capital S, of P and Q as well. Sorry. Then I split my goal, because I have here if and only if, and if and only if is actually conjunction, so I split. And then I, concerning the first goal, so I like to use these bullets to structure the proof, but it's not required. You can write everything in one single big scope. And so here I move the antecedent of this implication to the context using the intro. Then I destruct H, and here I'm using the destructive tactic to say that, okay, if there is an X such that this is true, assume that this is true for a given, an arbitrary X prime, then I destruct again H, but in this case a different destruction. Here I'm saying that I want to prove this goal, but consider that just P of X prime is true, and the second one is consider that just Q of X prime is true. So I have these two goals. In this case, you should know that H1 says that P of X prime is true, and here I have a disjunction, so I say I want to keep just the left hand side. Then I instantiate this predicate, so I say the witness. So if there is an x such that is true, suppose that this x is this x prime here. So I say exists x prime. So I instantiate the x in the goal. Oops, sorry. And I'm left with p of x prime, which is exactly h1. So I just apply. And the other cases are pretty much the same, but manipulating different parts of the goal. The second one, I'm left with these negations, or I have with not p, and if I unfold the negation in h2, I'm left with p implies false. But if I unfold the negation in the goal, so the goal is not p, but remember that not p is actually p implies false. So now I can move the antecedent of this implication to the context as well. And then now I can apply for the reasoning, apply h1 to h3 to derive q, and then apply h2 to h3 to derive false. And it's a contradiction, and the proof is finished. Okay, so now let's resume. Now I'm going to talk about other tactics. As Volker has already noticed, you have a common vocabulary of tactics. So rewriting, simplification, these are quite common in different proof systems. So we have already seen simplification. So if you want to prove that for every natural number, 0 plus n is equal to n, let me go to that. The simplification works here because of this. If you print the added definition, so the definition of this symbol, is defined by partner matching on the first argument. So add is defined as, if given two natural numbers, if the first one is 0, then add of 0 to anything is going to be the second natural number. However, if n is a successor of some p, then adding n to m is going to be add p to m and then computing the successor of this number. So note that here, since here the first argument of the add is 0, by partner matching, the simplification can reduce these to n. However, if we had this, the simplification wouldn't work. Because, again, if you see the definition of add, well, the first argument here is not 0. It's a successor of some number. So, in this case, depending on how you define your functions, the simplification is going to work or not. Another very common tactic when you're proving things is rewriting. So here in Coq, we have this rewrite tactic. And so suppose that you have in your context some hypothesis saying that some expression is equal to other expression. In Coq, you have this syntax. You can just say rewrite h, and as I said before, by default, the tactics are applied to the goal. So if you say rewrite h, supposing that h is an equality, it's going to rewrite in the goal every occurrence of the left expression considering the second one. But then we can say explicitly the direction of the rewriting, so you can write these arrows. So when I say rewrite arrow to the right, I'm saying that substitute every occurrence of the left-hand expression writing the second expression. If I write this arrow in the other way, so the substitution is going to be in the other way. If you omit this error, by default is left to right. And you can also do rewrite in the context, say rewriting something in some hypothesis of your context. So in this case, I want to prove that if n is equal to m, well, adding n to the left side of the equality and m to the right side of the equality yields the same value. So when I want to prove this, I can say rewrite the goal, considering the hypothesis h in the direction left to right. So every occurrence of n in the goal is going to be rewritten by m. So u is left by m plus m is equal to n plus m, and then you can just use reflexivity. Other example can be seen here. So I'm assuming that n is equal to m is equal to o, and then n plus m is equal to n plus o. So you just need to figure out the order of rewriting you need to perform. So in this case, you can first rewrite every occurrence of n by m. So the left hand part of the equality becomes n plus m, and then I rewrite consider h2 but in the opposite direction. So the o occurrence becomes om, and now you can just use reflexivity. And this rewrite tactic, it works not only with information in your context. You can use previously proven facts to use rewrite as well. And now there is probably one of the most important comments in Coq, that's the third one, because I have a huge number of facts that have already been proven. And if you know how to use the search column properly, you can skip a lot of work just reusing what has already been proven. So here you have a first example of using this comment. So I want to prove that 0 plus n multiplied by m is equal to n plus m, n multiplied by m. So we know that 0 plus n is n. So I can say search in the database of proven things, something that in some place in the theorem I have 0 plus something. And when I do this, it says, okay, you have a theorem in this file saying this result, but you also have this theorem in this library. So as every language, Coq has a prelude, so there are some libraries that are automatically included in your specification. And for instance, this theorem that I have proved here is also in the standard library in Coq, in these libraries here. So since this theorem says that n plus n is equal to n for any n, I can use this theorem to rewrite my goal from the left to the right. So when I have here 0 plus n, using the rewrite tactic becomes n, and then I can prove this by reflexivity. Okay. So the search comment is extremely useful. Here you have some possible ways of using search. So you can search by a string, so search string and then you give the name of the string. And in this case it's going to search both for definitions and statements, theorems, examples, facts and so on, that contains the string name. If you search not for a string but for an ID, it does the same, but considering theorems or definitions in where you have a variable or something with exactly this name of this identification of this ID. And you can also search by a partner, as I showed here. So you can say search something where you have 0 plus wildcard. You can read more about search on these two websites because there are many variations of how to use the search command, but if you know how to use it, it's going to skip a lot of work, as I said. In calc, you can also prove things by case analysis. From now on, I'm going to use this syntax sugar. I'm going to write equal question mark, sorry. It's a syntax sugar for this definition, that's EQB. The difference, when you write that A is equal to B, the equality symbol is going to return a proposition, so true or false from the logic. But if you write equal question mark, this definition is going to return a Boolean variable, a Boolean value, and not the true and false from the logic. So if I have this theorem here that says n for any n plus 1 equal to 0, it is equal to false. So to prove this, if I try to simplify, the simplification does not work here because, as I have shown you before, the definition of the sum cannot be simplified here because the pattern imagine concerns the first one and the first argument is not 0, so it doesn't go further. And if you see the definition of this symbol, you're going to see that also how it was defined does not make possible any kind of simplification. So in this case, what you need to do is to prove this statement by case analysis of the possible values, of the possible formats of values of n. And then we use again the destruct tactic, but with a different syntax, slightly different. And let me bring Sinatra again here. So NOT is an inductive type with two constructors, O and S. And the first constructor takes no argument, whereas the second one takes a natural number and then gives another natural number. So when you say I want to perform case analysis considering some variable, I need to provide to this case analysis a list of lists where each list is a list of arguments that should be passed to the constructor of that type. So the natural number has two constructors. The first one is O, and it takes no argument, so this bar separates the lists within the big list. So in the first case, I have no argument, whereas in the second case, you need to provide a natural number such that the successor gives another natural number. And here I say, okay, this number will be an n prime. So when I destruct this, it's going to create two pseudos. The first one is considering that the n is the O, so it's the 0. And the second one, that n is actually the successor of an n prime. And you don't know anything about n prime. So in the first case, when you're left with 0 plus 1, you can perform simplification and then just reflect safety. And in this case, note that you're left with the successor of n prime plus 1 equal to 0. If you see the definition of the Boolean equality, you can see that it performs pattern matching in the first argument, n. So n here is the successor of n prime. N is not 0, right? It's the successor of some number, so it goes in this case. Then it performs pattern matching in the second argument. So in this case, I'm comparing this number with this number. So this number can be seen as a successor of some number, and the n is 0. So by pattern matching, well, if you're comparing whether the successor of any number is equal to 0, this is false, because false is not the successor of any number. So in this case, the simplification works because it can see that this expression becomes false, and then you can prove this by perfect safety. So the destruct here, the general form of the destruct for performing case analysis is you destruct, then you pass the name of an ID in your proof. Then you need to provide this list of lists, and each list contains the arguments you're going to pass for the respective constructor. And then for each constructor, a sub goal is going to be generated, assuming that the ID is actually a value constructor by applying the respective constructor to these arguments. So with booleans, you can prove a lot of things with booleans performing case analysis. So if you want to prove that the boolean negation of B, the boolean negation of the boolean negation of B is equal to B, you can prove this by destructing B, which is a boolean. And note that lists here are empty because both constructors of boolean values do not take any argument. And then it's just reflexivity. So many results you can prove by just performing case analysis. So if you want to prove that the Boolean version of the conjunction is commutative, you just destruct the variables involved in the comparison. So in this case, I destructed B and C, and here I'm using a command to say I destruct B and C at the same time, and then it creates 4 subgoals. Okay. And another very common tactic is induction. So suppose that you want to prove that for any natural number n is equal to n plus 0. Again, here simplification is not going to work due to how the sum is defined. Case analysis in this particular case does not have help as well, because when you destruct n, the first case is easy because, well, 0 is equal to 0 plus 0. But in this case, by the definition of the sum, you can simplify the right-hand part of this statement. So the successor of some number added to 0 is equal to the successor of the sum of n0 plus n. But then you are left with this, which is obviously true. But that simplification, well, unless you use the rule, the rewrite rule that says that n prime plus 0 is 0, you would not be able to go further. So one possible way to prove this is to perform induction. So in this case, the syntax for induction is almost the same for destruction, with the difference that you can name the induction hypothesis. So when I perform induction in n, the first case is going to be the base case, so when n is 0. And the difference here is that in the inductive case, besides rewriting my goal such that n is a successor of n prime, it also adds to the context the induction hypothesis that say you want to prove this assuming that n prime is equal to n prime plus 0. And then you can use your induction hypothesis to rewrite your goal, and then this can be proven by reflexivity. Okay? So let me go back. So trying to summarize the tactics we have seen so far. So we have all the tactics to do with propositions, so split, left, right, intros, and so on and so forth. You have these tactics for rewriting, so you can rewrite left to right, right to left. You can also perform case analysis doing destructs, and you can also prove by induction using the induction tactic. Now going back to the functional part of Gauss, as you expect of a functional language. Coq supports polymorphic data structures. So, for instance, a list is an inductive type, but parameterized by a type A. So, the constructor cons, it receives a type a list of A, and it yields another list of A. There are some syntactic details, like when you're writing polymorphic functions, you can, instead of using parentheses, you can use color braces to say to Coq that parameter is optional. So Coq inference system will try to figure out what should be the value of that type. So you can define things like repeat. So given a type x, a value of x in the counter, this function yields a list of type x, repeating the small x count times. So it's defined by pattern matching count. So when count is 0, it yields the empty list. Whereas when count is not 0, it yields x appended to the beginning of another list, where is the recursive application of repeat to a smaller number of count. So for instance, if I want a list repeating count twice, you get a list with 2 fours. So as usual, this is a syntactic sugar for no. Here I have the syntax sugar for cons, and the plus is the syntax sugar for append. And then you can define all these common functions on lists. So you can write unit tests, like the reverse of the list 1, 2 is the list 2, 1. Besides lists, you can also define polymorphic pairs. So pairs of two arbitrary values from different types. So the prod is actually it's an inductive type with just a single constructor called pair, and it receives a type A, a type B, and it yields a pair of a value of A and B. So here you have in the slides main examples of definitions of functions, of recursive functions on pairs, lists. I think you can read the details later. They are pretty common on functional languages. So this function combine, it receives 2 lists. The first one is a list of x, of type x. The second list is a list of type y, and it returns a list of pairs combining each value of each list. You can also write functions that receive as arguments order functions, so higher order functions. So filter is a function that, given a test, that is a function that for a value of capital S, x, it gives a boolean, a list of x, and filter returns a list of x containing the elements that satisfy the test. So for instance, if you filter this list by the function even b, you get the list with just 2 and 4. You can also define anomalous functions. So instead of, if there is a very simple function you want to use and maybe not reuse later, you do not need to create a definition, give it a name, and then use these. You can create anomalous functions using the fun keyword. So in this case, I'm filtering this list of lists by a function that, given a list L, if the length of this list is 1, it's going to return true. So if you filter this list of lists, you get the list with the list 3, 4, and 8. So you can define all these stuff like map, folder, and these classical functions you have in functional programming. So as I said before, I'm going to skip the hands-on section too, and I will proceed, and then we have all hands-on session then. In code, combine this idea of polymorphic functions and the idea of proposition, you can write functions that returns propositions. So in this case, I have a function called in that given a type a value x of a, and a list of a, basically this function yields a proposition that's going to be true if and only if x is in this list. So it's important to say again that this definition could not be used to extract the code because it's returning a proposition and not a Boolean value, right? So in this case, I'm going to show you the two. I'm going to prove this statement, so in for this list is true. So when I simplify here, so simplify is going to compute the definition of in that will actually create this statement. Because in is a recursive definition, if the list is empty list, it's false. And if it's not an empty list, if it's the test whether x prime is equal to s, and then disjunction of a recursive call for in. So again, in for this list becomes this proposition. And to prove this proposition, here you can see the parentheses, but it's right associative, so suppose that consider this or the other part. So when I say right, I get rid of 1 equals to 4, so I get, this part. If I do right again, I'm left here, and now I want this equality. So now I say left, and I get rid of the rest, and now this is true. Okay. I'm going to come back to this in definition to show you how you can write the same kind of proof in a more automated way. So here's another example of proof using in but in a more complex statement. So here I'm using struct, I'm using rewriting, reflexivity. You can use in to prove more sophisticated things like for all types A and B, for all function from A to B, for all lists of A's, given an X from A, if X is in L, then it's true that the application of X of F in F will also be in the mapping of L considering F. Because map is that function that will apply F to every element of L. So this is quite intuitive that this is true, but then we can use calc to prove this statement, and this proves it's become more interesting. So I will explain this one step by step. So I perform here an inverse instantiation of A and B, of F0, of L, and of X. So I get all of these here in my context. And now I'm going to do an induction considering the list L. So when I do induction, I'm left with two possibilities. So the base case, when the list is the empty list, and by simplification, this becomes false implies false. And to prove this, I move the attachment of this implication to the context, which is a contradiction, and then I can prove this using inversion. The second case, now I'm assuming that L is a list appending X prime to the beginning of L prime. So to prove that, I perform some simplification. So the simplification is going to compute the E definition. So X in this list is actually if X prime is equal to X, or if X is in L prime. Now I move this statement to the context. Since it's a disjunction, I destruct it. So I will need to prove the same statement, but in the first subgoal, consider that this is true, and in the second subgoal, considering that this is true. In the first case, I can use H to rewrite my proof. So when I do this, every appearance of X prime will be substituted by X. Yeah?
What is the difference now that you use the plus instead of minus?
I use oh yeah, sorry. There is a hierarchy, so minus would be the first level of subgoals. If you are in a subgoal and you have subgoals for this subgoal, you have plus. If you want to nest, you can use a cross. If you want to nest more, you can start using curly braces for as many times as you want. Right. So here I perform rewrite. Oh, sorry.
But that's mostly convention, right?
Yeah.
You can use plus. You could have used plus.
Yeah.
Minus.
So when you rewrite, you get this, and this is strictly true. So I say left. So I get rid of the right part, and then by reflexivity, this becomes true. Now in the second case, I will get rid of the left, so I say I want to stay with the right part. And if I apply the inductive hypothesis, so here I'm doing a backward reasoning. I mean, if I want to prove this, and I have this statement say that this implies the same thing of my goal, I'm left with the need to prove H. I could have done this in the other way around using forward reasoning as well. And now I can just apply H, and this proof is finished. So it seems not very difficult, but when you are doing this by yourself, it becomes a little bit difficult because you need to remember all of the statics and see how to proceed. One thing that is interesting in Coq is a theorem can also be seen as a kind of a function. So if you recall the Curry-Howard correspondence, I'm not going into the details of this idea here, but there is a correspondence between the proofs and programs, and the practical consequence of this in Coq is that a theorem can be seen as a function, and as a function you can call a theorem by providing arguments to that, and what we would get is an instantiated version of that theorem for the arguments you provided for each bar. So here's an interesting case. Suppose that we want to prove the commutative of the sum considering three variables. I had a proof suppose that I had the proof that for all n and m, n plus m is equal to n plus n. So you already have the proof that the sum is commutative, but for two values. If I apply here this theorem, the first argument is x, and the second argument is y plus z. So when you apply this, it changes. So you're left with this. But recall that here you have the first argument is y plus z, and the second argument is x. So if you apply the same theorem again, you go back to the first state, because you cannot see that you are applying the theorem considering that y is the first argument and z is the second argument. But what we can do, there are many ways to solve this problem, but one way is plus com can be seen, as I said, like a type of a function, a kind of a function. So if I say plus com, which is a theorem, provided y and z, this actually yield for me instance of the theorem where the first argument is going to be y and the second argument is going to be z. So plus com applied to y and z is the fact that y plus z is equal to z plus y. And I can use this equality to perform rewriting. So if I rewrite, consider the result of the instantiation of this theorem for the particular variables y and z, I get what I want, and I can prove this reflexivity. Okay. More tactics. I said before that Mohammed asked me about some properties about constructors, and this is, I said at the time, constructors are injective functions. So if you have something that Sm is equal to Sm, since S is a constructor and the constructor is an injective function, it's as a consequence you get that n needs to be equal to m. So the inversion tactic, that's a problem of, not a problem, but it makes the process harder, is that each tactic has many ways of being used. So I have seen the inversion tactic to be used to conclude a proof when you have a contradiction, but you can also use the inversion tactic to reason about the injective property of functions. So if you have an equality such as n is equal to Sm, and you apply inversion to H, it derives a new hypothesis saying that n needs to be equal to m, since S is a constructor, and all constructors are injective functions. And besides generating this new hypothesis, the proof system automatically rewrites your proof flow from the left to right. So all the occurrences of n in the goal are substituted by m. So note that before I had n is equal to m. When I apply inversion, my goal is now n is equal to m, which I can prove by reflexivity. And this works not just for natural numbers, but for any kind of constructor. So if you have that at least that n followed by m equal to O followed by O, if you apply inversion in H, you get that n is to be equal to O and n is to be equal to O. And the proof goes already rewritten considering these facts, and you're left with a equality that can be proved by reflexivity. Another application of the inversion tactic is when you have, let me show this slide. If you have a hypothesis saying that the application of the constructor 1 to expression 1 is equal to a different constructor applied to any other expression, since these constructors are different, this is a contradiction, right? Because constructors, besides being injective functions, the images of these functions are adjoint. So you can't have any value that belongs to different types. So in this case, when I perform case analysis considering n, I get here, for instance, false equals to true, and then I apply inversion. The proof is finished because false is one constructor, true is a different constructor, and there is no way that two constructors applied to an expressions would yield the same value. And one last bit of using destruction to perform case analysis is that you can also perform destruction not only on variables but on expressions itself. So suppose that you have this very simple function that says if n is equal to 3, you return false. If n is equal to 5, you return false, else you return false. So this function always returns false regardless of n. So if you want to prove this, you can perform case analysis not in n, but in the expression n equal to 3 or not. So here is similar to the example Thierry showed. So you want to prove x, and where x is any expression. So you have two cases: a case when x is true and a case when x is not true. So when you do this, you're left with two supposed. The first one is you assume that n is equal to 3. So by simplification, in this case, this function should return false. And in the second case, you get this expression. Because if n is not equal to true, then you get this. So the first case is trivial. In the second case, you can perform again case analysis on this expression. So if n is equal to 5. And then you have two cases. The first one is trivially proved by reflexivity, as this third one as well. So the message is, besides using destruct on these junctions, besides using destruct on IDs, you can also use destruct on compound expressions as well. The problem is that sometimes when you do destruction on compound expressions, sometimes you lose information because what is being destructed is lost in the process of proving your goal. So here is a version of that function where it returns true if n is equal to 3 or 5. And here is a theorem that says if n, if this function returns true, then n needs to be odd. And this is true. But the problem is when you make a case analysis destructing this expression, the first case you need to prove that if true is equal to true, then odd n is equal to true. But you know anything about n because n, the information that n is equal to 3 is lost during the destruction process. So there is another variation of this song where you use this keyword EQN and then give name. In basically what it does is it performs the case analysis destructing the expression, but it creates a hypothesis in our context, recalling the information associated to what is being destructed. So in this case, when you destruct this compound expression and you say that record this information in this hypothesis, you're left with this goal, but you now have this information that you're considering in this case that this expression is equal to true. And then you can manipulate this information to abstract that n is an odd number. So in this case, if you apply this theorem, this theorem says that for any two natural numbers, if the test whether they're equal use the Boolean true, it means that they are equal. So here's the Boolean version, here is the logical equality. And then you can rewrite this Boolean comparison to the fact that n needs to be equal to 3. Now you can rewrite using h, so odd n becomes odd 3, and by simplification, this is a true. right? So as you can see, there are many topics. Okay. The next topic I would like to talk is about these getting into more details, considering the difference between define something in the functional world, define something in the logical world, and a third possibility that is define some proposition using inductive definitions. So I have shown you the definition, this definition of given B. Well, so suppose that given B is a recursive function that given a natural number n, if n is 0, this function returns true. If n is 1, this function returns false. And if n is the successor of the successor of some number, this function is going to return even b of n prime, so of the predecessor of the predecessor of n. So here you have a functional definition, a functional test for whether a natural number is even. It's also possible to define the notion of being even using propositions. So, supposing that you have a function that given a natural number n, this function returns the double of this natural number n. If a number n is even, it's because exists a k such that n is a double of k, right? So here you have a definition of being even, but this definition is not a functional definition, but a logical one. And these two definitions are actually the same. So you can prove, for instance, I will go back. So you can prove that for any number, if even b is equal to true, so is this first even b is the functional one. So if you compute this function called even b applied to n, and this function yields the Boolean value true, this happens if and only if the logical definition of even b is true. So this theorem is relating these two words, the functional definition of being even and the logical definition of being even. In the previous slides, you have the proofs of auxiliary facts you need to prove that theorem. And so you might be asking yourselves, so is it better to define something functionally or in a logical way? Well, it depends. The functional definition is good because you can embed it in other functions. So you can say, if the computation of this function yields true, you do something, false, you do otherwise. So since every function in calc terminates, you can embed the functional definitions to test whether a behavior you want to observe is observed or not. On the other hand, the logical definition is better in proof context, because if you have a definition that n is equal to m, so if you have the logical statement saying that n is equal to m, you can perform, for instance, rewriting. So if you know that n is equal to m, you can rewrite using the rewrite tactic. However, if you have the functional computation of whether n is equal to m yields true, you cannot use rewrite in this context. So there are benefits on defining something in a functional way or define something in a logical way. And depending on what you are defining, sometimes you cannot define this in a functional way, but only in a logical way. And sometimes one of these two forms are easier than the other. And there is still a third alternative that is define a property inductively. In this case, I'm defining this EV that is a property whether a number is even or not. But here this inductive definition is different from the previous ones, because note that in the previous definitions I didn't have an argument for the inductive definition. So you can see these constructors like operational rules you can use to prove something. So suppose you want to prove that 4 is an even number. So the second rule says that for any natural number, if n is a natural number, the successor of this number is also a natural number. So applying a backward reasoning, if you want to prove that 4 is an even number, if you apply this constructor, so here I can see these constructors as theorems. So if you apply the EV as constructor, you are left to prove that n is even. So here I want to prove that 4 is even. When I apply that constructor, I need to prove that 2 is even. Because recall that this constructor, that's a different constructor because it's a kind of a theorem, it says that for any natural number, if n is even, the successor of n is even. So if you want to prove that 4 is even, this is proved if you prove that 2 is even. And to prove that 2 is even, you just need to prove that 0 is even. So if you apply this constructor again, your goal becomes 0 is even. And this is exactly what this other constructor says. So now you can apply this other constructor to finish the proof. So I showed you very briefly this idea that you have these 3 ways to define properties in Coq: using logic, using inductive definitions, and using functional programming. And the take-home message is, if you want to create something that is computable, so you want, for instance, to extract code from your specification, you should pursue the functional perspective. On the other hand, the functional perspective might not help you in your proofs, because, for instance, it's not going to allow you to manipulate these facts as logical facts. So what I commonly see is that a property is typically defined in both ways, or in all 3 ways when possible, and the equivalence of the definitions are proved. So if you are in some context when you need one or the other, you can skip from one to the other using the proof of the equivalence between them. Actually, this is partially what I did in that example here, when I had this hypothesis saying that the Boolean test where n is equal to 3 returns true, and I used the theorem saying that for any number n and for any number m, if the Boolean test says that m is true, it's because the logical fact that n is equal to m is logically true. So this back natural theorem allows me to rewrite this expression like n is equal to 3 in this particular example. Another topic I would like to talk is about proof automation, but don't get too excited about the automation itself. If I properly understood Volker's question during Thierry's lecture, uh, the difference between what Thierry was showing about automation is that Thierry showed that algorithm, so you need to prove some property. So you try to have some heuristics to find in your uh, database the facts that are close to what you want to prove, and there is some strategy to try to manipulate your goal and your hypothesis in order to try to prove a goal. But there might be some way to prove that, but the choices the algorithm make might not find the way, am I right? And then this proof is not proved completely, and you are left to add facts or manipulate the proof in order to conclude the proof. The proof automation in code is very simple. So basically, it's you use some decision procedures to simplify facts, but you do not have any kind of heuristics saying that, well, I have many possibilities. I will try this one that seems to be better, but if it fails, okay, well, I leave this as something that needs to be proven by hand. So you don't have anything like a sledgehammer from Isabel. So you have this static, for instance, called auto. But what auto does is it searches for a sequence of applies that will prove your goal. And by default, it's going to search just for 5 applications of apply. So it's a very short state space search. If you can increase this number, you can say out to 100, but then this will easily take forever because it doesn't have any kind of heuristics of saying, okay, this path seems to be more promising than that one. It's like brute force, so it's going to try combinations of applying the statics, and this is exponentially, so it's not very clever way. So here I have some examples of theorems that can be proved just by auto. So this theorem, the transitivity of implication. So if P implies Q and Q implies R, you have that P implies R. You can prove these by doing apply H2, apply H1, apply H3, but you can also prove this fact saying just auto. As I said, there is a limit for the search. By default, the search is 5 applies. So in this other example, that's basically the same, but with a bigger chain of implications. Auto does not solve the goal, but if you say auto 6, it solves the goal. There is another automation tactic called T-auto. It implements a decision procedure for intuitionist propositions that are tautologies. So basically, I think that most of the proofs that I showed you on the logical part, all of them could just be proved by T-auto. There is another automation tactic called omega. It implements a decision procedure for a subset of first-order logic called Presburger arithmetic. I don't know whether you are familiar with this concept, but basically you can have sums, subtractions, multiplication by constants, inequalities. So you have a very restricted form of expressions. But if this is the case, omega solves the goal if it's solvable, and does not solve in the other case. Another perspective of automation in Coq is what is called tacticals. So tacticals is kind of a high order tactic. So it's a tactic that receives another tactic as an argument. So one example of a tactical is a try tactical. So you say try something, and it applies, well, it performs the tactic something, and if it does not succeed, it leaves the goal as it was before. There is this other tactical called repeat. So when you say repeat T, it's going to apply the tactic T until it fails. And it's important to note that the functional galena, the functional part of coq, so every function you define galena terminates, but this is not true for the proof language. So if you are in any proof, and don't do this, but if you write repeat, simplify, that is going to crash, because the simplified tactic can always be applied, because if it simplifies the goal, it simplifies. If it can simplify the goal, it leaves the goal as it is, but it doesn't generate an error. So if you do repeat simplify, simplify is going to be repeated forever. Well, not forever, but until your stack, you get the overflow over stack. But yes, and another interesting tactical is the semicolon. So the semicolon is a tactical, right? And this meaning of the semicolon tactical is, yeah, well, this is one possibility, there are others. In this possibility, I apply the tactic T, and the tactic T might or not generate such goals. And then I apply T prime on each sub-goal generated by T. So, do you remember that proof? Suppose that I want, it's a slightly different proof. Suppose that I want to prove that 10 is within this sequence. But 10 is the last element. So I need to simplify and say right, until I reach the 10 is equal to 10, and then I perform simplify. I can rewrite this proof saying this. I try to pick the left option, so see here that when I simplify the indefinition, I get these propositions. So 1 is equal to 10, or 2 is equal to 10, or until false. So what this proof is doing is, I try to pick the left hand side of the left element of the disjunction, and then I do reflexivity. If these two tactics succeed, and remember that the reflexive tactic only succeeds when the proof is completed, my proof is finished. However, if try left reflexivity does not work, I'm left with the same goal, and then I do right. So if I delete this repeat here, what this tactic is doing is trying to pick the left. So left is 1, oops, sorry. Left is 1 is equal to 10, and then it tries to do reflexivity. But it does not work because 1 is not equal to 10. So when I say try left reflexivity, it performs the statics, but since it does not prove the goal, it leaves the goal as it was. If I put here a right, I'm saying that I perform the first combination of statics, and if the goal is not proven, I'm left with some sub-goals, and then I'm going to apply right on each sub-goal left. Indeed, the left application of this try left and reflexivity for the first case leaves me with the same sub-goal, and then when I say right, Oh, sorry, I need to simplify. I don't need to simplify, I just forgot the dot. So when I say this thing, it performs right. But now if I embed this in a repeat, and I need to be confident that 10 is within the sequence, it's also a goal. Because it will just keep repeating this idea that is, I pick the left and check whether I finish the goal. If I don't, I apply right, and then I do this again. Another possibility for automation with Coq is a language called LTAC. So this is the third language of Coq. So the first one is Galena, the functional one. The second language is the proof language. And the third one is LTAC. And LTAC allows you to define the tactics by partner matching, by many things. So here is a very boring proof that says for any function that receives a Boolean value and yields a Boolean value, if I apply this function 3 times to any Boolean, the result I get is the same if I apply this function to this Boolean 1 time. So it's an interesting fact, right? So for any function you can figure out that receives a Boolean and yields a Boolean, if you apply this function 3 times, it's the same as applying this function just 1 time. If you want to prove this, this is a quite boring proof because you need to perform a lot of case analysis whether FB is going to return false or whether FB is going to return true, and you need to keep record of the cases, so you need that EQ and keyword. And if you take a look in the proof, you're going to see that there are some symmetry or some similarity between the cases. So you can see that here you have rewrite H1, rewrite H1, rewrite H1, reflexivity. You can see that you have in this branch a very an equal idea. So rewrite H1, reflexivity. So here I did rewrite H1 3 times. Here I'm doing 2 times. Here I have H2 2 times. Here I have H2 2 times again. Here I have rewrite H1 followed by rewrite H2. Yeah, so there are many similarities between these cases. I'm not going to get into the details, but I can define in LTAC this static. So I say LTAC, and this name is going to become a new static in my proof environment. And this static receives an argument, B, and it performs partner matching in the goal, the state of the goal of my proof. And the partner matching is, if I have an hypothesis saying that anything applied to B is equal to anything, here's the entanglement here is the separation between the context and the goal. So you can write here many things, and this will be the partner matching concerning the state of your context. Here you can also perform partner matching depending on the state of your goal. So if this partner matching, so if you can match with this structure, I say that I'm going to rewrite this H. So basically, the start is analyzing the state of my context, picking the hypothesis I need to prove my goal, and rewriting using these hypotheses. And now I can rewrite that previous proof, saying that I destruct F considering both situations, so F true and F false. I also destruct B. B is the argument, and I can perform some sequences of rewriting, and this proof is completed. In my opinion, I have seen many examples, well, not that many, but some examples of tactics being defined with attack and using these ideas of tacticals. And my impression is you get very short proofs, but they're not readable. But well, they are shorter. And the examples I have seen, in most cases, the people first write the bigger proof, then it figures out, okay, I can rewrite this in a smaller way, and then the smaller way is written. Right? And to conclude, and then we can spend some time doing exercises, you need to be aware of some limitations due to fundamental decisions when Koch was implemented. So the Koch's core logic is based on the calculus of inductive constructions, which differs from many other formal systems like Zermelo-Franken set theory. For instance, one example is in set theory, you can, for instance, in B, you have the set of natural numbers. You can find in B another set, which is a subset of the natural numbers. And you can have a variable that belongs to two different sets. In Koch, any value belongs only to a single type, because the way you construct values, you need to use constructors, and the constructors, the images of the constructors are disjoint. So in Koch, in B, you have the set of natural numbers. You could use set comprehension to define the set of even numbers, and to know whether a number is even or not, you could test whether this number is in this set. In Koch, you can do this. You can have the set of natural numbers and define a subset of natural numbers. So you need to define a functional way of computing whether a number is even, or use some logical definition or some inductive definition. So this is just one difference to mention many. All the differences is like a functional externality is a concept that's not part of Koch's logic. Another example is the excluded middle rule. So P or not P is not in the Koch's core logic. So you can't prove using just the Koch's core logic anything that depends on the rule that P or not P is true. But you can extend the logic. And to do this, you can just define axioms. So you can define axioms, for instance, for functional externality. But you need to be really careful because of this. Never ever do this. You can, for instance, create an axiom saying that for any proposition P, P is true. And then you can prove that if P implies Q, this is true if and only if Q implies P, which is an absolute. And you are going to be able to prove this in Koch. So here's the proof. There is a difference. When you were doing the exercise, you saw the admitted keyword. And when you have something that's admitted, the two highlight these in yellow. But the admitted idea is, okay, this is something I'm assuming that is true, But I'm also saying that I plan to go back to this and prove this fact. When you axiomatize something, it's going to be something that you believe to be true, but you're not going to prove this in the system. But the tool also highlights the axiom in yellow. So to prove this absurd fact, I can perform a split, so the if is a conjunction. And in this case, I introduce, I do interest, so I move P implies Q and Q to the context. I'm left with P, and my axiom says that for any proposition, P is true. So this is true. And in the second case, I'm left with Q, but my axiom says that for any P that is a logical proposition, P is true, so I cannot write again. And my theorem is proven in Go. So, what I have already read about this is you need to be really careful when you are extending Coq's score logic. There are some extensions that have been proven safe, not in Coq, but in other systems. So you can use excluded middle in many cases, but there are some combinations that are not safe. So to mention one, Coq has a definition for set middle in many cases, but there are some combinations that are not safe. So to mention one, Coq has a definition for set middle in many cases, but there are some combinations that are not safe. So to mention one, Coq has a definition for set middle in many cases, but there are some combinations. So some combinations, if you're depending on how you are interpreting sets, you cannot add to your core the principle of excluded middle. So for instance, you can prove in Coq, you can't prove in Coq that not P implies is equivalent to P, because to prove that you need to rely on the excluded middle property. And to finish, I would like to show you some more interesting application, everything I said before. So you can, in Coq, define what's called a model type, which can be seen as a specification. So here I'm defining what I say, dictionary. Define what's called a model type, which can be seen as a specification. So here I'm defining what I say, dictionary. Define what's called a model type, which can be seen as a specification. So here I'm defining what I say, dictionary. Define what's called a model type, which can be seen as a specification. So here I'm defining what I say, dictionary. Define what's called. I'm going to have some functions, but here I'm not saying their behavior. I'm just saying that the insertion function, it receives a key, a value in the dictionary, and it yields another dictionary. I have the get function that receives a key, a dictionary, and returns a value. Actually, an option, because if you don't find the value, you're going to return none. And then you can write down, specify properties that needs to be satisfied by your dictionary implementation, regardless of how you're going to implement the dictionary. So for instance, I don't care whether you are implementing your dictionary as a list or as a tree, but if you insert a value associated to a key in the dictionary, and then you get the value associated with this key, you should get the value you have just inserted, right? So you can specify properties you want your abstract data type to satisfy, and then you can create implementations. So here I say that I'm implementing a dictionary based on lists, and now here I have to provide concrete definitions for all of that elements. So in this case, my key is a natural number, my value is a string, my dictionary is a list of pairs of keys and values, and so on. And so every parameter that's needs to become or a definition of an entity or a function, and everything that was axiomatized needs to be proved. So you need to prove that for your definition of dictionary, if you get the value associated to a key just after insert this value, you get the value you have just inserted. So I think this is very interesting because you can write down what is you have as the expected behavior, and then you can write implementations and check whether they are valid implementations for your specification. And my last slide, you can also generate code from your specification, remembering that code is going to be generated just from something that is computable. So you can extract this for Haskell, for Congo, and you just import this library called extraction. You say which language you want to extract, and when you run this last command, you get Haskell code. And so if I do this, so let me go to the end. And I perform this extraction, says okay, this Haskell file was created. And note that here it's extracting all definitions you have in code that are necessary to the concept of dictionaries. So it extracts the notion of natural numbers, the notion of pairs, the notion of lists. So you have the guarantee that the things you are manipulating relies on your original definitions. The problem is, for instance, this definition of natural numbers is not efficient, because if you want to compare whether the two natural numbers are the same, it's a risk call that will go back until 0. So during this extraction process, you can say, okay, I want to extract from this formal specification, but I want to use the natural definition of Haskell because I believe that this definition is correct. So you can then optimize your code and so on. So, so the comp proof system has many possibilities, but it's very hard work. So the proofs tend to be quite long and difficult, very commonly. But well, there are benefits in doing this. So there are other tools like, for instance, the prover embedded in AttenDB, other theorem provers, and in my humble opinion, I think that's a trade-off you're going to take. So if you want a higher degree of automation, you typically restrict to what you're going to be able to specify in that language. So here you have this high order functional programming. You can instantiate theorems. So we have a very powerful language, but on the other hand, you don't get too much automation. So I think you need to reason about what you want to formalize, what are the power of the language, of the specification language you need to deal with, and then choose the one that is expressive enough to formalize your concepts that provide the best of automation you need. So there are many materials to study more about cock. There's this series called Social Foundations, and there are many books and online reference where you can get more information about cock. So I would like to thank you very much. There's too much information to say about cock in not that time. But well, thank you very much for your attention. And I think that now we can use some time to do the hands-on sessions we had skipped it, if you want to, or well, we can do that. So thank you very much.
What would be the next exercise?
So we have covered until hands-on, the first one, hands-on session, that was about the functional language and logic. The second was easier. So we did this first hands-on session that was about the logic and the functional language. There is the second hands-on session is about the structure, the induction, the involved topics, and defining polymorphic things in cock. The third hands-on session is about the idea of defining propositions using functions. And the fourth and last hands-on session was about proof automation, so using articles and define something in a functional, logic, and inductive way. So we stopped, it's just the first one, so we should go now to the second one. So the first exercise of hands-on session 2 is to prove that not in B, not in B prime, and not in B 2 prime are equivalent.
CSP.